I can see why you'd think this is broccoli, and that's because it is broccoli. But if you look a little bit closer, you'll see that there's a miniature broccoli hidden within the broccoli. We call this broccoliception self-similarity, a characteristic property that emerges from simple, repeated rules that create fractals. Fractal self-similarity appears everywhere in nature. Instead of encoding each intricate detail individually, which would require enormous genetic information, nature cleverly repeats basic patterns, constructing complex structures like leaves, trees, ferns, shells, and well, broccoli. But to actually see those things, you'd have to leave your screen. And who has time for that? You've got to get your 8 hours of screen time. Every pixel on your screen maps to a coordinate. So how do we trap an artificial fractal inside that grid? One way is by playing the chaos game. To play the chaos game, you need to blindfold yourself and point to a random coordinate, throw a three-sided die, pick the transformation associated with the number you rolled from a list, apply this transformation to your coordinate to get a new coordinate, and at this new coordinate, draw a dot. Now just repeat this process thousands of times. And a self-similar fractal pattern emerges called Sierpinski's triangle. The shape looks cool, but it's kind of plain, and we need beauty for that sweet screen time retention, so let's fix that. One way we can make things more beautiful is with color. We can introduce color by giving each transform a color index C, a number between 0 and 1. As points bounce through the system, they now carry their color with them, gradually blending it with the next transform's color using this formula. Once the final color index is calculated, we feed it into a color palette function which maps values from 0 to 1 to a color. We now have color, but things still look a bit flat. And that's because, currently we just override each pixel with a new color each time the pixel gets hit. If we count the numbers of times a pixel gets hit and scale its color by it, we get something much nicer. We can do this with log density plotting. There's one more noticeable tweak to make things less flat. Gamma correction. Without it, the image looks either way too dark or too washed out. And with it, the colors look the way that our eyes expect. At this point, you can mess around with random transformations and create beautiful, colorful fractals. But how do we design things more intentionally? We need to look at our transforms more closely. These transforms are affine transforms, described by formulas like this one. Let's apply one to a coordinate and see where it ends up. Now, to really understand what these transforms do, we need to apply them to a group of points. Let's sample points in a unit square and apply our transform. Now we see that applying this transform actually rotates the points. By using different values, we can achieve translation, scaling, a sheep, and a sheared sheep. You now have all the ingredients to start making intentional compositions. Take the approximate bounding box of your composition and transform it to form your composition. This way we can, for instance, create a fractal. Our fractal now consists solely of affine transformations. These are a fine type of transform, but not great. So can we use more interesting transforms? For retention, we need something edgy, like a square. This is the formula for the square transform. Instead of transforming the x and y input, this transform involves randomness. On its own, it just forms a square. But when we combine this square transform with an affine transform, we can rotate, translate, scale, and shear the square just like we saw before. We need one more affine transform to build a blocky broccoli, or Pythagorean tree. Trees have leaves. To make leaves, we'll have to introduce transform probabilities. We need 4 transforms that together form the so-called Barnsley fern. Let's render it. It vaguely looks like a leaf, but it leaves some room for improvement. Fern leaves are actually called fronds, and so far we haven't made any good fronds, because each transform was chosen with equal probability. But this time, with a smart choice of probabilities, a beautiful fern emerges in full glory. Okay, this looks cool, but can we get even more interesting fractals? The answer is yes. Currently, the probability distribution is the same regardless of the previous transform. But by assigning each transform its own probability distribution for selecting the next transform, we get more interesting patterns. Let's look at this fractal I call squaring the circle. Kinda boring, right? By changing the transition probabilities, you get something that is different, but not the same. Now we almost have fractals that can maximize viewer retention, but they take quite a long time to render, and you just get one image. How is one image supposed to keep up viewer attention? How can we animate these fractals in real time? The answer is with a pixel shader running on the GPU. In pixel shaders, each pixel runs the same small program in parallel on the GPU. In our case, the Fractal Flame algorithm, and then outputs its results to a shared buffer. Sequentially, it takes quite a long time to fill even a small buffer, while in parallel, the fractal emerges much quicker at a higher resolution. We then post-process this buffer with our log density scaling and gamma correction, et voila! You can now watch your screen the entire day. We've improved our artificial fractals a lot, but it can always be better. Screens only have a limited resolution, unlike reality, so maybe look up from your screen once in a while and admire the beauty that is all around us. Like this wild fern that rendered itself without a GPU in real time on a supermarket.